Okay, so this is a long title, and first of all I want to thank, of course, first of all, Professor Shahnaz, who organized this, and I think she deserves a big round of applause for organizing this meeting. And of course, the University of Berkeley and all its leadership and all its faculty and all its staff that is helping us. So what I will be talking about is, okay, page down, is the following thing. Everybody knows Professor Zadeh as the father of fuzzy logic, and there will be a lot of talks about that. What I'm planning to do has nothing to do with, well, okay, has something to do with fuzzy logic, but I'll emphasize that we can view Professor Zadeh as a pioneer in three things. One is probably non-controversial, he is pioneer in AI, and two, maybe surprising, he is a pioneer in statistical analysis, and he is a pioneer in foundation of mathematics. And again, while most of the people in the audience are probably fuzzy, but the goal of this talk is to convince non-fuzzy talks and to explain to them what we do. And I also want to emphasize that he was a true citizen of the world, and I view it in a positive sense. So how did he become a pioneer in AI? It started with a very practical problem. Lotfi Zadeh was started as a specialist in control and systems, and his textbook on linear system theory was a classic. Everybody knew his book, everybody used his book. This is like, I don't know, maybe the algorithms book now, which is everybody uses. And it provided optimal solutions to many important control problems, optimal within the existing models. But surprisingly, mathematically optimal did not lead to very good results. Why is that? Not optimal results. Sometimes you have an optimal control which seems to be optimal, but when you look at it, it's sometimes worse than when the humans operate. How can it be? And so something was missing, and so Zadeh asked experts what was missing. And his answer was, okay, sorry. So what happened was they got an explanation of what was missing, but that explanation was not in precise terms. That explanation was in terms of words from natural language. For example, how do you drive the car? An expert driver can say if a car in front is close and the car slows down a little bit, then a driver should hit the brakes slightly. So, of course, ideally, how would the traditionally people in AI would do that? They would say, okay, that seems to be a reasonable rule. Let's try to formulate a precise rule out of that. So how do you get a precise rule? You ask an expert. If the car is 5 meters close, it slows down from 60 to 55 kilometers per hour. So you press the brake, right? Yes. With much force. And for how long? And of course, nobody says, I press the brake with the force of 2.3 kilonewtons for a duration of 500 milliseconds. They say, I press the brake slightly for a short period of time. How do you translate that? The problem is, of course, the answers are not precise. So what we can do the following thing. What happens normally if the answers are not precise? Well, if somebody says, well, what do you do? Well, approximately 1 kilonewton. So you take exactly 1. Sometimes somebody else says 1.2. And as a result, when you implement the force exactly, you get some weird control, which is often much worse than when a human drives. So instead, we can apply optimization. For example, we can say, okay, here is the model, here is the passenger, it weighs whatever, 70 kilograms, it's so you get an optimal control. The problem is, if the passenger loses a few pounds or gains a few pounds, or another passenger enters the car, the problem changes. And so what was optimal before stops being optimal. Third option, of course, is to ignore expert rules, as many people did. And again, it's not the optimal solution. So what did Zadeh propose? What Zadeh proposed was a revolutionary idea. Yeah, and there's an additional thing. As already was mentioned, it's not clear what we want. We seem to be very precise and exact in what we want, but in reality, we don't. Like, for example, when you ride on a train, we want a smooth ride. But what does smooth mean? It's still not clear. It's a very complicated thing. Engineers have been trying to formalize that, but when you would think smooth is like, I don't know, integral of square of the second derivative, it doesn't perfectly fit with what we perceived as smooth. Our perception is very complicated. So what Zadeh has an idea is this way. In case we can only extract imprecise knowledge from the expert, instead of ignoring these rules, what we can do, we can develop some techniques that transform these rules into precise control strategies. And this is what he called fuzzy logic. Now, okay, sorry. So I'll just give a very simple example, and I apologize for those of you who are in fuzzy logic, but kind of I'm trying to get this as an explanation for everybody else, and then I'll switch to how it is a pioneering in any other disciplines. So let's consider a very simple example, a thermostat. I had a similar problem yesterday when I was in my room. It was kind of surprisingly warm. I had a sweater with me, but it was very warm yesterday, so I tried to figure out how to operate it. I couldn't exactly, but the whole idea is if you turn the knob to the right, the temperature increases. If you turn it to the left, the temperature decreases. And our goal is to have some comfortable temperature T sub 0. So if you ask an expert does not say, okay, if the temperature is 5 degrees higher, you turn 3 degrees to the left. No, the expert says, if the temperature is practically comfortable, what do we need to do? Nothing. If the temperature is a little bit warmer, turn a little bit to the left. If it's a little bit higher, turn a little bit to the right. Now, how does that work? In terms of the difference, it means if the difference is negligible, the control is negligible. If difference is small positive, control should be small negative, and so on. And we can, of course, use the abbreviations. We can make it sound like mathematical rules, but of course, it's not mathematics. It's an abbreviation for something imprecise. And then we can say a control is reasonable for given x when either the first rule is applicable, which means what? The difference is negligible, control is negligible, or the second rule is applicable, which means the difference is small positive, control is small negative, and so on. So how do you translate this statement into the precise formulas? So first of all, we need to explain what this means. Then we need to explain what and or means, and then we need to generate some control based on this information. How do we do that? So first stage, how do we interpret x as negligible? In traditional properties like x greater than 5 degrees or whatever it is, the property is either true or false. And negligible means what? To some people, 5 degrees is negligible. I had a friend who liked to say, Vladik, if you feel cold or hot, that means what? You need to go to the gym. A true macho man, well exercised, will never feel anything. He only feels good about himself and about the world, okay? To others who are more realistic, well, if you change by 2 degrees, you already feel it's a little warm or cold. So, and there is no exact threshold. So what we can do is, again, I always have trouble. I'm a wrong person doing fuzzy because I have trouble every time they say on a scale of 0 to 10. But when students evaluate us, they have no trouble. On the scale of 0 to 4, how good is the professor? 3.2, 3.3. And surprisingly, it's consistent. It makes some sense. Good professors usually good bad evaluations, bad computers have bad evaluations. So if you evaluate something like a 7 on a scale of 0 to 10, you just put 0.7. It's not a probability. It's just some statement. That way, we get the degrees of what it means for every x. What does it mean x is negligible? What it means u is negligible, and so on. And ideally, now the next step is to estimate the degree of the combined statement. What is the degree to which x is negligible and u is negligible? So again, a natural idea is to ask the expert again. But the problem is, for every value x, we can ask the expert. That's not a big deal. But if we consider all pairs, all triples, and so on, we get a lot of possible statements. Like even if you have 3 n basic statements, we can have billions of possible combinations. There is no way we can ask an expert. So we end up with the need to do the following. We need to estimate the degree to which a combined statement is true based on the degrees to which individual statements are true. And this is, by the way, one of the misunderstandings. I'll talk about that later. So we have some algorithm according to which we produce some estimate for the degree to which A and B is true. And this estimate is called an AND operation, or for historical reasons, a T-norm. Sorry. Okay. So what are the properties of the T-norm? A and B means the same as B and A, so therefore this operation should be commutative. A and B and C intuitively means the same as this thing, so the operation should be associative. Of course, it should be monotonic, and there should be reasonable properties like true and true is true, and so on. And this is a known classification of all such operations. In particular, what we can do is, for example, if we additionally require that A and A means the same as A, then we have the only operation is minimum. And this is one of the most widely used operation. Another is the product, and so on. Same thing we can do with OR operations, also known as T conorms. And then if we require that A or A means the same as A, we get maximum. Otherwise, we get other operations like A plus B minus AB, produced by Zadeh himself, and so on. So, and then finally, once we have this, we can use these rules to produce the degree. We combine the rules to produce the degree to which U is a reasonable control for X. And then we need to generate a single control value. So how do we do it? Well, a natural idea, although not the only possible one, is to use the least squares. And I'm not kind of ashamed to say that. This is a normal statistical method, and nothing wrong with using it, and it's definitely valid way beyond statistics. So if we use least squares, what we can do, we can use these as the weights, or we can use some combination of this as the weights. And then if we minimize this, we get the formula which is known as centroid diversification. And this whole technique, this whole 3 steps, which is kind of a very simple algorithm, leads to many successes, some of which have been mentioned. You have fuzzy-controlled trains, fuzzy-controlled elevators, which provide the smooth ride. And again, why fuzzy? Because otherwise it's difficult to formalize what people want. We have fuzzy rice cookers, which provide tasty rice. And again, I'm not the right person to taste that, because for me, any food is good. But there are people who are very picky and who can distinguish between the good quality food and average food. To me, if you know me, I eat soups from the cans. I like them. Okay, so of course this is a very simplified description. In reality, that's why kind of it's a whole area of science. It's not just a simple algorithm that people use. So what are the simplifications that were made? First of all, I mean, we say, okay, an expert says 7 or 8 on the scale of 0 to 10, but the same expert who cannot tell with what force he or she presses the brake, of course, cannot tell exactly 7 on the scale of 0 to 10. Okay, he may say 7, but if you ask on the scale of 0 to 100, there is no way. So 70, 71 is kind of indistinguishable. So what can we do is we can say, okay, there is like the whole interval of possible values that an expert may indicate, because 71, 72 is kind of the same. Or better yet, we can say how confident it is. Okay, 70, 71, reasonable, 69, maybe, and so on. So we get a fuzzy degree. It's called a type 2. And this leads to control, which is actually not only closer to the expert's control, but also better in many cases. It's smoother, it's more stable, and so on. It better reflects what people do. And this is what the next speaker, Oscar Castillo, will talk about briefly. Second, centroid diversification doesn't always work. Let me give a simple example. Suppose you have an obstacle in the road. The rule is you can turn to the left or you can turn to the right. So you have 2 possibilities. And if you apply centroid diversification, because of the symmetry of the problem, you pick one number. This number will be what? Smack into the middle. So of course, this is not the right approach. It needs to be modified. So take into account that we only select controls for which the degree of confidence exceeds some threshold, and so on. Third, we often have some additional constraints. For example, when we talk about smoothness of control, we're not just using everything. Okay, so maybe if there is some billionaire from whatever, Saudi Arabia wants to have a smooth ride, money is not a problem, energy is not a problem, anything else is not a problem. If we're talking about the train that is run by the city, it has to be limited. There are some constraints on cost, on energy, and so on. And Finally, we want to not just have the expert rules, we want to optimize. And optimization under fuzzy uncertainty can also be described by fuzzy control techniques. That is actually the paper that Zadeh, Professor Zadeh and Bellman jointly wrote. Now, why this is interesting? So, okay, so this one more technical thing. Many people in engineering, many people in science do the technical things. Why would I, for example, as a trained mathematician, like it? Let me give you an example, explanation. So, first of all, of course, many of our important notions are fuzzy, like good or bad. Okay, if you listen to politicians, our side is good, the other side is bad. And it's kind of funny. At some point, I don't know, Syrian, I don't want to get into politics, but I'll give one example. The guys who are against Assad, right? First you read in American newspapers, the angel with wings. Assad is the only bad guy. Now it turns out some of them are Islamic State, they're even worse, right? But in reality, if you watch BBC.com, none of them are angels and none of them are complete devils. They have good and bad sides. So it's a matter of degree. Same thing, causality. What is the cause of the event? There are many different factors that affected this. And how do we describe this fuzziness? In general, in applied mathematics, there are 3 levels. Well, there may be more, but I'm just simplifying it. 3 levels of applications. First level is what most people do. You have mathematicians by training, you have engineers who know one formalism very well, and they use it everywhere they do. And often they are very successful. If you're a statistician, you use statistics. If you're a specialist in differential equations, you use differential equations. If you're a specialist in stochastic differential equations, you apply it to whatever you want. You apply it to robotics, you apply it to finance, you get great results. Fine. Then there is second level. Second level is people who know several degrees. And then they select one degree which is most appropriate. And sometimes they are better because they can see, okay, in this case, we can apply differential equation, we can apply difference equation, we can apply stochastics, statistics, which one works better. But the final best level is when the researcher designs a new formalism. Instead of using one of the previous mathematically known formalisms, the researcher designs a new formalism specifically tailored to this problem. And that's kind of an interesting philosophical question. There was a Nobel Prize winner, Wigner, who wrote about a paper in 1950s about unexplainable efficiency of mathematics. And he said, well, there is some mystery in the world. You take mathematics, which is a very abstract discipline. Stanislav Lem, who many of you know is a science fiction writer, had a book called Summa Technologia, similar to Summa Theologia. And he wrote that mathematicians are like crazy tailors. So you make a suit for somebody who is shape of the ball, somebody who is the shape of the cone, and you prepare those suits, and then one day aliens land on Earth, and they are of the shape of the ball. And you are perfect. You think, okay, this suit suits, that's how mathematics apply. But in reality, mathematicians often are useful. For example, quantum physics is perfectly described by something abstract mathematical called Hilbert spaces. General relativity shows that space-time geometry is perfectly described by what? Pseudo-Riemannian geometry. Why is that? Why is this abstract mathematics suddenly useful? Well, the true answer is that in reality, this is the wrong impression. Hilbert spaces were not known as Hilbert spaces. They were invented by John von Neumann when he wrote a book on foundations of quantum mechanics. Pseudo-Riemannian spaces were not known before Einstein started working on general relativity. There is no such thing. He invented this new mathematical formalism to handle space-time geometry. And Zadeh's idea followed the same patterns. Before Zadeh, researchers described human uncertainty how? By using the known math. And the most typical math for describing uncertainty is what? Probability theory. So he uses probability theory. And in some cases it works well. In some cases it doesn't. What Zadeh had is a new technique which is specifically designed to describe that uncertainty that is not covered very well by the existing probability theory. And as a result, he got many successful applications. So he is, in my viewpoint, on line with quantum physics and general relativity from the viewpoint of applying very interesting mathematics. Okay. there is a difference. Hilbert spaces are, to a non-mathematician, complicated. Pseudo-Riemannian geometry is complicated even for many mathematicians. Zadeh's theory is simple, but in mathematics, simplicity is good. If you can come up with a simple model, nothing wrong with that. It's actually the good thing. Misunderstandings. Of course, there was a lot of misunderstandings which caused all this trouble. Some folks falsely believe that in fuzzy logic, this degree of A and B is uniquely determined by the degree of A and degree of B. Of course, this is not true, which can be easily disproved. So the purpose of fuzzy logic is not to claim that you have truth functional logic. No, it's an approximation. It's a way to approximate, to describe approximately these things. Second, some people falsely believed that Zadeh always recommended min and max. We in the fuzzy community know that's not true, but people don't read, people don't write. So already in his first 1965 paper, he said explicitly that we should use other operations as well. And he had example of product and A plus B minus and B, and he explicitly mentioned that other operations are sometimes more appropriate. Third, some believe that Zadeh wanted to replace probability with fuzzy logic. We know that, people don't. No, he never had that. He said that it's like let 100 flowers bloom, following the famous saying by Chairman Mao. He always wanted to say that in some cases probability is better, in some cases fuzzy is better, and the proper way is to combine these formalisms. Now comes the more controversial part of my talk. Zadeh is a pioneer in statistical analysis. Why I'm saying this? Fuzzy is kind of a generic word. It could mean, on the scale of 0 to 1, it could also mean subjective probability. So, and this is a very typical situation. In many cases, we know the probabilities of different individual statements, and we would like to know the probabilities of different Boolean combinations, like E1 and E2. And again, how do we describe that? Well, to describe all possible probability combinations, it's sufficient to consider, for example, AND combinations. And if the events are independent, that's easy. We just multiply these probabilities. But what if they know that they are not independent and we don't know what is the dependence between them? What is the traditional approach? Traditional approach is to assume some prior distribution. That's a usual Bayesian approach. Now, what's wrong with that? Nothing wrong with that, except different priors lead to different answers. Of course, if you have a lot of data, it eventually converges, but in practice, we often don't have enough data. So what do? How do statisticians do it? Statisticians usually select the distribution for which is the easiest to process, easiest to compute. And it makes sense, especially in the old days when computers were not that powerful. But of course, the problem, real life is often complex, so why would we select the simplest method to work necessarily true? So Zadeh's idea is the following. And this is something that can be described in purely probabilistic terms and in which he was a pioneer in doing that. So what he is saying is this: let's select some appropriate AND operation appropriate for the given area that would transform the probability of A and probability of B into the probability of A and B. And there are natural requirements like that it should be associative, commutative, and so on. And the corresponding AND operations should be experimentally determined. And that's all he said. And that's actually a big thing in probabilistic approach. This is actually a formalization what people did in Mycene. Mycene is the world's first expert system which was designed to diagnose rare blood diseases. And what Stanford folks who did that, they actually spent a lot of time and a lot of effort and a lot of money on figuring out which AND operation best describes the human reasoning. And then they thought, fine, just like Boole did, we found the laws of human reasoning. They made emycene, empty mycene, which they thought would be applicable to all possible reasoning in the world. And then they applied it to the next thing. Of course, why medicine? Because in medicine there was funding. The next thing where was funding was geophysics. So they tried to make a geophysical system, and it was a big failure, because in geophysics people reason differently. And again, they have a different AND operation. It makes perfect sense, because in geophysics, you face a strict competition. So if you have a small probability that there may be oil in this area, and the competitors are jumping on you, you better start dealing, because maybe you lose money, but you don't want to lose the opportunity. In medicine, if there is a chance that a person has some appendicitis, you don't cut him right away. You make a lot of tests. You don't want to start cutting until you go, and this is kind of leads to complete difference in the end operations. And same thing in many other areas. So you have end operations which are individual, and of course in mycin they do it empirically. What Zadeh did was have a formal, precise description, a technique that could do it consistently without having to reinvent the wheel every time. Third, Zadeh, a pioneer in foundations of mathematics. Why is that? From the logical viewpoint, from the purely mathematical viewpoint, what Zadeh did is something that Professor Lukasiewicz in Poland did in the 1920s. So he had, instead of a two-valued logic, where you have two values, true and false, he had the logic in which possible truth values can run through the whole interval. But what he did is, first, he succeeded in transforming this abstract theory into a very useful practical tools. And two, he came up with the idea how to generalize this to the whole mathematics, not just to simple logical formula. And the idea is very straightforward. The idea is the following. For example, you replace, every time you have a formula, you replace and correspondingly for all, because for all is what? It's just infinite and, right? For all people in this room, that means for me, for Professor Shahnaz, and for others who are sitting in this room, something is true. Replace with, for example, min or some other end operation, and replace all with maximum. Let's give two examples. How do you extend a data processing algorithm to fuzzy data? That's a very reasonable approach. Every time you have a new formalism, you have to think of how to extend it. At first glance, it's a creative problem. You need to think about it deeply. You need to write a PhD about that. No, the Zadeh's formalism can go straight into the answer right away. So what does it mean that y is reasonable? It means if you have the relation between the corresponding quantities, it means there exists x1 through xn, such that x1 is reasonable, x2 is reasonable, xn is reasonable, and y is equal to f of x1 through xn. So now what do? We replace and with minimum. We replace there exists with maximum. And what we get, and the degree to which x1 is reasonable, it's what we described in fuzzy as the value of the membership function. So you get what is known as Zadeh's extension principle. That's it. And instead of min, we can use other operations. We can get modifications. So what I'm saying is that it's not like, okay, you know, sometimes you read the papers, you get the false impression. Why are we using this formula? Zadeh said. Well, Zadeh is not Jesus Christ, I put it this way. He said, who cares? I mean, the problem is, it's not that he said that. Why did he say that? Because this is a result of a direct application of his general approach to a very natural definition. So it's not Zadeh's extension principle because he came up with this formula and he's a genius. Of course he's a genius, but this formula comes because it's a general application of his technique. Same thing in intuitive continuity. Continuity, of course, everybody's spoiled by mathematicians. What is continuous? For every epsilon, there exists delta, blah, blah, blah. But this is a formal mathematical definition. When engineers say something is continuous, they don't mean that. What they mean is if x and x prime are closed, then f of x and f of x prime should be closed as well. Now, what does that mean? How can we describe that? Closeness can be described by sum of the input by some membership function. Closeness of outputs may be described by a similar function, but the scale may be different. We can have our scaling coefficients. And what does it mean A implies B? Well, kind of first approximation, we can say that our degree of confidence in A should be at least as large as the degree of confidence in B. We write this down. What do we end up with? We end up with Lifshitz condition, which kind of is needed in mathematical analysis of control and comes out of nowhere with like a saying, well, we would like to do it in general, but without Lifshitz condition, we cannot prove it. But this is indeed, according to Zadeh, a correct formalization of the intuitive notion of continuity. And there are many other examples like that. And finally, a warning, and this is, again, one other controversy which started by Professor Elkan, who is a big specialist in AI. He mentioned, but kind of was a controversial because the problem is, of course, that we start with a logical formula, we translate to min and max, but we have to be very careful because classically equivalent formulas lead to different results. Simple example, A or not A. Of course, in fuzzy logic, in classical logic, it's equivalent to true. In fuzzy logic, it's not. If you have like 0.5, you have maximum of 0.5, and 0.5 is different. So you have to select an appropriate formulation. You cannot just use any of them because they're not equivalent. And finally, the true citizen of the world. Who was he? And luckily, we're not fighting against us as people fight against other famous people. But like, for example, Al-Khwarizmi, you know, the guy who invented, after whom the world algorithm was known, he was born in Khwarezm, which is now Uzbekistan. So, and the reason why he invented the word algebra, al-jabr, and the reason why he was so successful in this is, in the old days, now, if you want to go from Uzbekistan to Berkeley, you take a plane and fly. In the old days, it was several months, and maybe the big bandits will rob you on the road or something. So you cannot just send an email and ask, what did you mean, Professor Khwarizmi, in this book? It has to be very, very clear. And so he wrote the book in which everything was so clear that anytime somebody would praise somebody from being clear, they say it's as clear as in the book of Al-Khwarizmi. So that's where the word algorithm comes from. Who is Al-Khwarizmi? If you ask somebody in Uzbekistan, who was he? He was from Uzbekistan, right? Now, what language did he write? He wrote in Farsi, because that's the language that people speak there. So if you ask Iranian, he was an Iranian. And again, everybody. It's like Hitler, nobody wants to own him, but Al-Khwarizmi, everybody wants to own. Same thing with Professor Zadeh. Everybody wants to own Professor Zadeh. To people from Azerbaijan, he's a national hero, which is absolutely correct. To people from Iran, he's a great Iranian. He stayed in Iran for 17 years. He graduated from the university. He spoke Farsi with a native. To people of Russia, he's a passionate person. You ask him every time. He knows more about Russian politics than most of us, and probably more than more Russian people. He was passionate. He had opinions. He had ideas. He helped people in Russia. And in the United States, he was as passionate in United States politics. And by the way, with his wife, he spoke English, although he could speak any other language. So who was he? To many people, he was her own. And this, in this sense, in my opinion, he was a true citizen of the world. Not citizen of the world in the sense that I'm above struggle, all your national things, they are not. No, no, he was passionate about everything. To everybody, he was his own. And he was passionately happy about successes of everybody as if he was own. And he was passionately against the injustices no matter where they are occurring. He may be very passionate, he may be very cool in scientific discussions, but when it comes to helping others, he was very passionate. And he was the embodiment of, again, of the statement of Apostle Paul, there is no Jew and no Greek, we're all one. He was the one. That was his attitude to nations, that was his attitude to people. So he had this attitude, take everything as a compliment, which was a little bit controversial, but you probably know him. It helped him a lot. He promoted his fuzzy ideas, but never at the expense of others. Vice versa, he always emphasized the need to combine them with others, with probabilistic, with neural, and so on. And so as a result, he inspired what is called now computational intelligence and soft computing. He inspired the World Congresses on Computational Intelligence, where neural, fuzzy, and genetic are combined to the extent that some sessions are jointly organized by several things, has journals on soft computing, has applications of soft computing, has many things. So in short, I'll just end with one more phrase. The world needs more people like Lotfi Zadeh. Thank you very much.
Because my talk was changed to the afternoon, so sorry for you, Hariana, but we have time for questions, and we can remember Professor Zadeh always said, don't hesitate to disagree with me. He was one of his phrases when he talks, so don't hesitate to disagree with Professor Vladik in this time, so we can ask or comment on his talk.
What was the most memorable truism that you ever heard Lotfi state?
Sometimes when he really didn't like something and disagreed, instead of saying, he kind of started saying like, well, it's not exactly the way it is, and I forgot the exact formulation he used because he used different ones every time. And he starts slowly, it's like Socratic way, moving you step by step towards understanding the true things. Like for example, I thought, when I started working, I thought that all fuzzy degrees can be described in terms of subjective probability, because I personally don't understand this on a scale of. But he convinced me that for many people, this is a very reasonable way. And the way he started is not by saying, no, you're wrong. That's most people will start. He's saying, well, there is some truth in that, but, and this but, I think, is his truism that, that I liked. And later on, I started to appreciate it. Every time he would say, but, I knew that something very meaningful and very important would come.
Any other comment or question to Professor Vladik?
Okay. Well, thank you.
Did you ever get a sense from Lotfi as to how important he viewed type 2 fuzzy logic relative to type 1 fuzzy logic?
Lotfi, you know, every time a new idea appears, and fuzzy logic was no exception, there is a trend. I forgot there is even a name. First, it is overhyped, and then there is like a backward reaction. Lotfi was always very good in emphasizing that neither fuzzy logic nor type 2 are the panacea for all the things. So my feeling of talking with him about this is that this was part of his general idea of let 100 flowers bloom. Of course, of this, he didn't say that. He cited Chairman Mao. But type 2 definitely is not a panacea. It's not that we should immediately stop doing type 1 and start doing type 2, as initially said. On the other hand, it's not a dead end, as some people start thinking after it went down. It's one of the main ideas that helps. I think, in general, he was very pragmatic. He believed in what is good for applications, like the proof of the pudding is its eating. So in many cases, type 2 helps, great. In some cases, type 2 doesn't lead to successful, meaningful improvements, so let's not use it. I don't think he was philosophically minded about these things, yes.
Yeah, I think we should mention him to introduce the concept of membership function, and also later on he introduced probability. That somehow, you know, you can normalize the components into 0 and 1, okay? And then you can have measurement of similarity on the some formed coordinates. Because the classical theory, statistical theory is based on the components, not on the membership function and probability.
No, I agree. So, but Professor Zadeh, as Professor Shahnaz mentioned, published hundreds of papers, in most of which he introduced new exciting notions. I am just scratching the surface. I was just telling, my goal is to explain to non-fuzzy folks how, in addition to being a very important contributor to fuzzy, he also was, could be viewed as a contributor to AI, to statistics, and to everything. But I agree with you 100%. A lot of, I didn't even mention a lot of things that he did, which are great contributions to fuzzy. Yes, absolutely. And we will today, during this whole symposium, we will hear a lot of things about different aspects, and unfortunately some people couldn't come, like Z numbers is another great idea, when you don't just have the probability of fuzzy value, but you also have degree to which you believe that this number is good. This was supposed to be a talk, but I think it was cancelled because the speaker could not come. But there are many, many exciting ideas, I agree with you 100%, that Professor Zadeh had.
To read his opinion about for this. This question really is not aware whether I am American, Russian, Iranian, Azerbaijani, or anything else. I have been shared by all these people and cultures, and I feel quite comfortable among all of them. But Lotfi was a very great person, very great friends. For your question, who is Lotfi?
Excellent citation. Thank you very much. Thank you. Thank you.
I think any other comment or question? No? Yeah, sorry.
What was your first aha moment with Lotfi? If you can recall when he did the Socratic questioning with you and you suddenly had this aha moment where you realized that this was the way to move forward.
Okay. My first aha moment was without Lotfi, when I was reading his papers. I was living in Russia, and I was working at the Institute of Electrical Measuring Instruments in 1980s. And Leon Reznik, who is now in Rochester, he was working on analyzing the airplane engines. And his boss, Putsima, he asked me as a mathematician, he said, you know, Leon Reznik is using some nonsense called fuzzy logic. As a mathematician, can you please look at that and see what the heck is going on there? And before that, my knowledge of fuzzy logic was more on like nice, interesting philosophical thing. Actually, we had to study Marxist philosophy in the Soviet Union, but our professor was very kind of realized that we don't exactly like Marx and everything, so he said, why don't you do some presentations on philosophy of mathematics in general? And I kind of found papers which were translated into Russian, and so I looked at Zadeh's papers. I liked them. I thought they were nice, interesting, but at that time I was not familiar with applications. And with Leon Reznik, we started looking into the applications. We looked at the Zadeh's and others' papers, and that was my first aha moments when I realized it's not just something to describe how people reason. This is a way to describe how to actually control the engine of the airplane. So I ended up telling to Putsima, it's not nonsense, it's vice versa. It's something that we should do, and we ended up doing some improvements on that particular control of the engine. So that was my first experience. And also, indirectly I met, we had a, well, okay, it's a long story, but in Russia, the system was like this. You defend your PhD, but you have to be officially confirmed by the central, not Central Committee of the Communist Party, but the Central Attestation Committee, okay? And High Attestation Committee, right. And since I'm Jewish, and Jews were kind of not exactly welcome in the Soviet Union, I was called to this Higher Attestation Committee to defend myself. And there I met a colleague, Vlad Dimitrov, who was originally from Bulgaria, who also came to defend himself, because he also defended dissertation. And we spent a lot of time, because there was a lot of us called, and we had look, and he had a dissertation on fuzzy logic, and Lotfi Zadeh himself wrote a letter to this attestation committee explaining how good is Vlad Dimitrov's job and everything, and that was another aha moment for me where I first read something individually from Professor Zadeh. And then, of course, when I came to the US, I started going to many different conferences, and I realized in fuzzy conferences there is this spirit of friendship and welcomeness that is not always welcome at research conferences. Yes, there are disagreements, but people are not attacking each other as viciously as sometimes used to be in probabilistic community, where there is a big fights between Bayesian and non-Bayesian folks, or even sometimes in AI communities. And yes, there were strong disagreements. I mean, scientifically, I cannot say that everybody agreed on the same thing, but the atmosphere was much more welcoming to the newcomers. So I think that kind of answers your question. Yes.
I think we would like to thank Professor Vladik, and he's also a very good example of someone that is well-known and friendly to people from all countries.
Thank you very much.
I think, thank you very much.
Thank you.